Okay, we're back. We're continuing with electron configurations and electron dot pictures. As you recall, at the end of the last video, we went all the way through oxygen. We got up to 8 electrons. You can see electrons, the electron configuration for oxygen's 1s2, 2s2, 2p4. Remember what that means is those 8 electrons begin by filling the 1s sublevel, and there's a pair that can fit there. Then the 2s, there's a pair that can fit there, and then we begin to start filling in the 2p, and we can fit 1, 2, 3, 4 electrons there so far. So that's where it goes, 1s2, 2s2, 2p4. Of course, we can fit another electron in here and here, and so we have a couple of more elements to go on that second period. In fact, the next element is fluorine. So fluorine has 9 electrons. Now, we know how the first 8 electrons are going to enter the atom, don't we? Yeah, they're going to do what the 8 electrons for oxygen did. So our question, of course, is where does the 9th one go? Well, that really doesn't make a difference. Remember, in the p sublevel, there are 3 orbitals, -1, 0, and +1, or, as we described in class, the px, the py, and pz orbital orientation. So far we have one here, or a pair here, excuse me, so we can't fit any more there. So we're either going to go here or here, and it doesn't make a difference. They have the same energy, but we like to do things in order, so we'll put it right there. So the configuration for fluorine, of course, would be 1s2, 2s2, 2p1, 2, 3, 4, 5. So 1s2, notice that 2 shows up as a superscript, 2s2, 2p5, which also shows up as a superscript. The dot picture. Once again, we're interested in the valence electrons, those on the highest energy level. And for fluorine, of course, that's the second energy level. And it has 7 electrons, 2s2, 2p5. So if we're to look at those again, the 2s is paired up. So we can draw a pair. I like to draw it on the right side of the atom first. And then we have our 3 2p orbitals, and there's 1, 2, 3, 4, 5 electrons there. So we have 2 more pairs. So I like to draw a pair on top and a pair on the side, and one all by its lonesome. There we go. So there's the dot picture for fluorine. Now we get to neon. Take a look at neon. Notice it's right at the end of this second row on the periodic table. Its atomic number is 10. So we're going to be dealing with 10 electrons. Of course, we know where the first 9 are going to go, and let's not kid ourselves. We know the 10th is going to go right there. So notice the 2s and the 2p are now full. 2s2, 2p6, along with, of course, those back in the 1s. So 1s2, 2s2, 2p6. So in my outer energy level, the 2s has a pair, and the 2p has 1, 2, 3, 4, 5, 6. So we have 3 more pair along with that pair. So we have neon symbol with a total of 4 pairs. And of course, 4 pairs is a stable configuration. So either a full outer energy level, like we had back here in helium, with just 2 electrons in the first energy level, or an energy level with 4 pairs, or a total of 8 valence electrons, is stable. Now, you might be a little nervous because I have a pair on each side of neon. What about the next element, sodium? Sodium, of course, has 11 electrons, 1 more than neon. Where am I going to put that next dot? Well, let's take a look. Here's sodium over here with 11 electrons. And so its configuration is going to be 1s2, 2s2, 2p6. Now let's look at our hotel diagram here. After 2p6 is full, we can either go to the 3s or 3p. 3s is lower energy, so we're going to put 1 electron there. So it ends with 3s1. So are you nervous about how many dots are going to be in sodium's dot picture? How many do you think there are going to be? Are there going to be 11 dots? If you think there are going to be 11, you haven't been listening. Remember, we're interested in the highest energy level, The third is the highest energy level for sodium, and there's only one electron there, so sodium only has one dot. If I were to draw the orbital diagram and the highest energy level, it's 3s1 with one electron there. Notice that sodium begins the third row on my periodic table, and it's the first element in that third row, so 3s1. Remember lithium? Lithium was in the first row, and it was the second element in that first row. 2s1 is what it ended with. And hydrogen, of course, ended with 1s1. Let's take a look. Sodium, and we have lithium, and we have hydrogen. Notice they all have one dot in their dot picture. Okay, now magnesium has 12 electrons total. So, I don't know what's going to happen next. We're going to pair up in the 3s, aren't we? So the configuration for magnesium is my 1s2, 2s2, 2p6, 3s2. So let's write that down. 1s2, 2s2, 2p6, 3s2. And what's the dot diagram for magnesium going to look like? Well, if we take a look at the 3s, which is the highest energy level, there's a pair in there. So magnesium will have a pair of dots. By the way, if you take a look at our periodic table, up above beryllium ended was the second row down, or second row across, second row down. It also ended with 2s2, and it had a pair of electrons. So let's find it. There's beryllium, a pair of electrons. There's magnesium, a pair of electrons. How about aluminium? 13 electrons. So let's take a look. And after the 3s is full, we're going to start filling up the 3p. So there we have aluminum's last electron. And so its configuration is 1s2, 2s2, 2p6, 3s2, 3p1. How many dots are going to be in aluminium's dot picture? If you said 1, you haven't been listening. It's the highest energy level, remember? The third is the highest energy level. So the 3s has a pair. The 3p, remember the 3p has 3 orbitals, -1, 0, and +1, has 1 electron in it. So the dot picture will have a pair of electrons and one all by itself. Notice aluminum is in the same family as boron. I'll bet boron had a pair and one by itself. Let's take a look. There's boron. It had a pair and one by itself. And we're going to get way ahead of ourselves, but think about what gallium will be in a few minutes. I'll bet it'll have a pair and one by itself. Turns out if they're members of the same family, they have the same ending electron configuration and therefore the same electron dot picture. All right. So that wraps up that page. Let's pull out the next one here. And we're going to go with silicon. And silicon has 14 electrons. Now we know where the first 13 are going to go. That's just like the 13 for aluminum, so the 14th is going to go here. So the configuration for silicon is 1s2, 2s2, 2p6, 3s2, 3p2. We can write that down. Are you guys getting fast at writing these down and predicting these configurations? And so we're interested in these 4 electrons in my dot picture for silicon. The 3s has a pair. And my 3p has 2 electrons. They go in by themselves. Remember, they don't pair up right away because it takes too much energy to do that. If these orbitals have the same energy, they'd rather be by themselves. So the dot picture for silicon has a pair and then 2 by themselves. So I'm going to draw one on top and one on the side. And that's our dot picture for silicon. Phosphorus has 15 electrons. So that 15th electron is going to go right there. And so it's going to end with 3s2, 3p3. So 1s2, 2s2, 2p6, 3s2, 3p3. We have the dot picture for phosphorus. It ends with 3s2, 3p1, 2, 3. Looks like there's a pair and 3 by itself. So a pair and 3 by itself. My guess is that phosphorus that we just did will have the same configuration as nitrogen. Should we check? So phosphorus had a pair and 3 by itself. Here's nitrogen from our notes, a pair and 3 by itself. Once again, if they're in the same family, they have the same ending electron configuration as far as S and P sublevels are concerned, and therefore they will have the same dot picture. Sulfur has 16 electrons. I'm going to make this a bit easier for us now. Haven't I been writing 1s2, 2s2, 2p6 a lot lately? So the powers that be have allowed us to take a little bit of a shortcut. Sulfur is right here on the periodic table. The noble gas before it is neon, which has the configuration 1s2, 2s2, 2p6. So what we do is we put the noble gas before it in brackets, and then we end the configuration 3s2, 3p4. Let's check to make sure. Yep, 3p4. That's what we're going to end up with for sulfur. So for the dot picture for sulfur, 3s will have a pair in it, right? 3s2. And those p electrons are 1, 2, 3, 4. We'll have a total of 2 pairs in the third energy level and 2 by themselves. So 2 pairs and 2 by themselves. And you can check oxygen. It's in the same family as sulfur, and it shouldn't surprise you that it has the same dot picture. Okay, chlorine has 17 electrons. So we're going to put neon in brackets. And neon is just an abbreviated way of saying 1s2, 2s2, 2p6. And then after neon, we'd have 3s2. And let's just check. Put another one here, 3p5 for chlorine. So chlorine's dot picture, we'll have 3s with a pair. And my 3p will have 1, 2, 3, 4, 5. 3p5, so we'll have 2 more pairs and 1 by itself. So a pair plus 2 more pairs and 1 all by its lonesome. And of course that's the same dot picture that we had for fluorine. Argon, well, that has 18 electrons. We'll put neon in brackets because it's the noble gas before argon. And we'll have 3s2, 3p6. As you notice, it fills that guy in right there. So argon's dot picture, shouldn't surprise you, has 4 pairs around it, just like neon. Okay, now are you worried about the next element? Let's turn this page over. Let's do another element. Let's do potassium, because that's element number 19. What do you think that's going to be like? You should stop the video and try it on your own. Alrighty, I claim potassium is going to be, let's see, that's atomic number 19. The noble gas before it is argon. So I'm going to put argon in brackets, and that's like saying 1s2, 2s2, 2p6, 3s2, 3p6. That's argon's configuration. And potassium includes argon's configuration plus another electron. Let's see where that next electron goes. In our hotel, you'll notice something strange happening. After the 3p fills, you would like to go to the 3d. The 3d is closer than the 4th energy level. And the 4th energy level is definitely further away. This is energy, not distance. But if you take a look, the 4s takes less energy to get to than the 3d. So the next electron would go on the 4s. So potassium would end with 4s1. Take a look. It's the 4th element down, 1, 2, 3, 4, in this S area, and the first element in that S area, 4s1. Now, once again, the idea is, I know in the 3rd energy level there are 3 sublevels, S, P, and D. The D is closer, but it's not easier to get to. Think for a second. Pretend you have two friends. That might be a tough one, but just pretend that you have two friends just for a moment. One lives 100 feet away. The other lives 200 feet away. Right? Logically, which one's easier to get to? Well, you'd say the one that lives 100 feet away, right? Well, the one that's closer isn't necessarily easier to get to. I didn't tell you this about your two friends. The one that lives 100 feet away lives up a sheer cliff, and you have to climb a steep, steep ladder to get to his house. But he's only 100 feet away. The one that's 200 feet away is just down the road from you. Straight. Now which one's easier to get to? Well, of course, the one that's farther away, because this guy requires more energy to get to. The same thing happens. Once we fill up the 3p, the 4s is farther away, but it's a spherical orbital, much easier for an electron to make than that cloverleaf orbital that you would see in the 3d. So that's why the 4s begins to fill next. So the dot picture for potassium just has one dot in it. Now go back and look at sodium, lithium, and hydrogen's dot picture, and you'll notice they're the same. Okay? We'll stop there. We'll pick up with calcium next, and we'll do a few more. Alrighty? Thanks. Bye-bye.